Welcome everybody to lecture 16, starting page 82. Now, there is a correction involved in the lecture notes on the upper half of page 83, and the portion leading to equation 175 had some typographic error, and that has been already forwarded to you as an attachment in email. Please correct the file accordingly. There is a sign error basically. Anyway, now we start by using the definition of E and B in terms of the scalar potential phi and the vector potential A. We have established by now that phi and A together constitute a 4 vector, and therefore the transformation of each component will be just like the transformation of the time and space components of a position 4 vector under Lorentz transformation. So in principle, this should give us the Lorentz transformation equations for E and B, something which we have written down without justification so far. So in order to build up to this, let us go to the so-called covariant notation, where things will be more obvious, because in this notation, any equation written with Lorentz scalars, 4 vectors, etc., are of such a form that the equation is valid in any Lorentz frame, even if boosts are made, and the appropriate values of the components of these 4 vectors, etc., modulo Lorentz transformation have to be used. That's all. Now, if you write the 4 vector A mu, which we have already written in terms of phi and A, you can define a quantity F mu nu as in equation 172. Del mu A nu minus del mu A mu. This is called a rank 2 tensor, which transforms like the product of 2 4 vectors. Product means all sorts of components are taken as products, kind of an outer product, but this is anti-symmetrized. So that F mu nu is equal to F mu mu, and this is 0 for mu equal to nu. This is called the electromagnetic field tensor, and the parts with indices mu and nu are 2 4 vectors. They are combined, and any transformation under a switch from the frame S to frame S prime will lead to the appropriate modification, or rather Lorentz transformation of the components of the 2 vectors, 2 4 vectors, del mu and A mu. Keeping this in mind, we know now, having learned that 4 vectors always Lorentz transform like T and X together, we can write down the Lorentz transformation properties of F mu nu explicitly, even if it requires some algebra. Keeping this in mind, we clearly show in equation 173 that F12 is nothing but Bz, taking the general definition of curl. Similarly, F23 is B1 or Bx, and F31 is B2. So basically the space components with mu and nu, none of them 0, basically yield as derivatives of the scalar vector potential the magnetic field. So these components of F mu nu yield the magnetic field. And a concise way of writing that is the way we have written it in equation 174. What about the electric field? The electric field is expressed in terms of F01. That is to say, electric field X is minus of F01, as has been derived in equation 175, where there were some sign mistakes originally and the corrected forms have already been mailed to you. But again, it is very simple, keeping the definition in mind that del mu has space component minus grad and time component del zero, and carrying out the differentiations appropriately with appropriate minus signs inserted where there was a mistake in the original version of the note. But the bottom line is that F01 is minus Ex, or Ex equal to F10 because F is an antisymmetric tensor. Similarly, F20 is Ey and F30 is Ez. Now, the electromagnetic field tensor F mu nu defined completely in terms of phi and A, which constitute a 4-vector, give us a clear prescription for the Lorentz transformations for E and B. We know how del mu transforms, just like the 4-vector that we have known. We know how A mu transforms. And therefore, when you go from S to S prime, you transform the components appropriately, including in the situations where we were testing the covariance of Maxwell's equations. Once you do that, you clearly obtain the Lorentz transformation properties of E and B, which we have written down without justification. The detailed algebra is just carrying out Lorentz transform things and taking multiplications of their various components. Such products will yield the Lorentz transform E as well as Lorentz transform B. This is a matter of straightforward algebra. That's why they have not been explicitly included in the notes. I would encourage you to carry out that algebra yourself and check against the standard forms of E and B transformations, which will be found not only in my notes, but also in umpteen other textbooks. This is where we end the contents of special relativity in the course, and we end with a few examples. First is a situation where at the bottom of page 83, an electron and a positron annihilate. In principle, electron, positron, photon interaction is there. So could they annihilate and go to a photon? E plus, E minus going to gamma. As you will see clearly argued, this is not possible. Why? In order to see that, you go to the center of mass frame of the system. There, the electron and the positron are approaching each other with equal and opposite momenta in the center of mass frame. So the initial 3 momentum is 0. So from momentum conservation, the final 3 momentum must be 0. And therefore, the photon must emerge with 0 momentum. But 0 momentum is not possible because 0 momentum would mean 0 energy, because momentum is h nu over c. And 0 energy is not possible because the annihilating electron plus positron must have a minimum energy adding up to the sum of their rest masses. That is to say, twice the mass of the electron, because the electron and the positron have the same mass. So therefore, energy and momentum conservation simultaneously is not possible if an electron and positron annihilate into a single photon. E plus E minus going to gamma is not allowed. Instead, they will at the minimum annihilate into 2 photons. The next example is that of Compton scattering, whose derivation I leave to you as exercise. It's a homework assignment because it's bordered with blue with 2 double lines on the left. But the basic thing is indicated. A photon, an energetic gamma ray photon, is hitting an electron at rest, which is moving away, and the photon is ricocheting in a different direction, making an angle theta with an angle in theta with the direction of the initial incident photon. If the momentum of the initial photon is not momentum, the wavelength of the initial photon is lambda 1, that of the final photon in general we assume to be different from lambda 1 is lambda 2. That is to say, the scattered photon in Compton effect has a different wavelength. In this case, just apply energy momentum conservation. Remember that energy of a photon is h times nu, the frequency. Momentum is h times nu over c. And using energy momentum conservation, in the notation c equal to 1, express lambda 2 in terms of lambda 1, as has been written in the bottom of that assignment problem. It is found in textbooks, so I'm not ruling out the possibility that you read them up and copy them, which is also okay, so long as you understand every step of the derivation. So, as far as course content is concerned, there is none left. In the remaining part, we have a few problems. For example, there is a problem about electrons in a projection television set and so on. There the solution is already worked out, and there is no point reading it out because you should at least make so much effort as to walk through this and convince yourself. Then there are 1, 2, 3 more exercise problems or homework assignments, some of them in parts, in pages 87 and 88, which are your assignments. So this is where we end the lectures on special relativity. And I may, when we come to this level, assign a few other additional homework problems, which will be assignments and which you can discuss with me later once you have submitted them, and of course with the TAs whenever it is convenient for you to meet. With this, I finish the discussion formally on special relativity, although we will carry out informal interactions through the rest of the course. Thank you very much.